Well, thank you so much for having me today. This is actually my first flight software conference. I'm really honored to be in front of you all. As much as I would love to say that trustworthy autonomy has been completely solved, I can't say that, unfortunately. So really what this brief is intending to do is start conversations. Unfortunately, the technology is just growing so much in complexity that our ability to actually assure these systems is just really not keeping up. And this, unfortunately, is not a single person effort. This is a team effort. And so the more conversations that we have and bring ourselves together to solve this problem, the better off we are. So let's think about the future. Where is autonomy headed? We're already seeing this from open source intelligence in Ukraine. Autonomy is already being used in conflict. The environment is changing. It's becoming more complex, more uncertain. There's a great brief, All Distribution A, from Dr. Kimberly Sablon, Trusted AI on Autonomy Roadmap. Highly recommend you check that out. But she has an initial slide where she really described the future of conflicts. And in describing that, she talks about things like essentially chaos, right? We're going to have lots of information coming from point A to point B. We're going to have contestedness. We're going to have denial, jamming. We're going to have spoofing. And so the complexity is ultimately growing, and our ability to rely on autonomy is going to become a necessity. And with that, it's going to be humans working with teams together, and the ability to have humans trust those teams is going to become a necessity. So keep this vignette in mind as we talk more about the complexities of the underlying problem of enabling trustworthiness. And so as you can see, not only is it the vehicles themselves, but also like open source intelligence. You can think about like gray zone warfare and so forth. Okay, so the way this talk is structured, I have more content than I have time, unfortunately, so I will be going a little bit fast, but I'd rather have time for questions, than to take all the time. So we're going to talk about some high-level foundations. We're going to talk about characteristics, what trust actually means, and what the challenges and what my personal recommendations are. I'll give you a case study on reinforcement learning and the oddities that it kind of presents, and then I'll talk about some trends and guarantees, ways that we can start resolving some of these oddities as we start leveraging more machine-learned autonomy and algorithms. So first off, I think we all kind of understand what autonomy is, but nobody can really agree on how to measure it. I mean, we've got the Sheridan scale of 0 to 10. We've got this SAEJ 3016, which I think is on 0 to 5, which is more geared toward like autonomous driving. So I'll quote the famous statistician Box, but I'll make it in my own flavor. All metrics are wrong, but some are useful. And so I actually think that this particular metric that was geared from Panos and Zeklis a few years ago really has three fundamental factors. The first being the underlying complexity of the goal and its underlying subtasks. Number two, the uncertainty and the dynamics of the environment. How chaotic is it? And then number three, the amount of human intervention necessary in order for the autonomous system to complete the underlying goals. Now, I want to clarify, intervention was used specifically, and I want to contrast that with interaction, because intervention essentially is it's allowing the autonomous system to be helped along, whereas interaction, I mean, that's the ideal, right? We want humans and machines to interact with each other, but we don't necessarily want the machine to rely on the human. So keep this in mind. I think this is generally a good metric to use, and there we go. And so when you think about autonomy, I think about just the vector magnitude, right? We have these three factors, and if we can take the vector magnitude, then that is essentially what I consider to be autonomy. All right, so diving into where is autonomy headed, and then what technologies are we reliant on in order to make this autonomy happen? So you can see some 8 characteristics. This is by no means exhaustive, but this is really what comes to mind when I think about modern autonomy. And you can see first off, collaborative and hierarchical. These things are forming teams, and they have to do it autonomously, and they have to establish hierarchies, right? We also have real-time adaptive behavior. These things are going out into the field, they're learning from their environment, what their adversaries are doing, and then potentially they're coming back and teaching next generations of autonomous systems how to operate. We're seeing increased perceptual understanding, so not just reliant upon the typical cameras, but radar, signals of opportunity, and other things like that, being able to best leverage the information sources that are coming from their environment. Self-awareness, introspection, being able to understand things like energy consumption. If these agents have to go out into the field, when do they need to come back and recharge? Can they maneuver in such a way that their vehicles won't brown out if they're leveraging some some modern GPU and then have to suddenly crank in the thrust. Advanced human interfaces, right? Because the machines have to talk to the humans, but what we're finding now, especially, is that machines are starting to talk English and other languages. And that obviously leads to its own problems, which I'll talk about in a little bit. Then we have the 3 Rs: robust, resilient, and reliable. I'll touch on these in a future slide. Multi-domain, these things are all going to be operating from space all the way down to deep sea. Some will actually be straddling the divides. And then lastly, scalability, modularity, and interoperability. We're going to have different vendors producing different autonomous systems, and they're all going to have to talk the same language, talk through the same ICDs and interfaces, and they're going to have to form ad hoc teams. Some are going to have to work with each other, and they're not going to know it until they're actually deployed. So those are what I see to be the characteristics of modern autonomy, and then the representative modern technologies. Our best friend, or maybe our best enemy, the neural network, right? These have been around for so long. It's led to this connectionist paradigm of artificial intelligence. And right now they're in a boom, right? Thanks to, ImageNet, AlexNet about a decade ago now, and just the amount of deluge of information, data that we have. These connectionist approaches are actually performing very well, but they're not explainable, which is one of the biggest issues with their deployment. So there's a lot of research going around on how to actually verify neural networks and how to make them explainable. And I'll talk a little bit about that. And then reinforcement learning, right? It's been the from a control theorist standpoint, reinforcement learning has always kind of been in the back seat. It's been an interesting oddity. And then the ML AI people kind of ran with it a couple of years or a few years ago. And I equate it to, they run around with a chainsaw, cutting down the house. And us control theorists are like, hold on, like we have good tools. We have formally verified techniques in order to do this. But nonetheless, it's hard to compete with something like AlphaGo, which, can play chess better than anyone else. So nonetheless, a big effort in the control theory community is actually getting guarantees for reinforcement learned and especially deep policies. Visual odometry, active SLAM, I mean, these two technologies have been around for a while, but they're still incredibly important to use. And this allows agents to better understand and perceive their environments, right? So here you can actually see a result from MIT's Chimera, which is a metric semantic approach to establishing what we call scene graphs of the environment. And so with these scene graphs, the agents can actually do what we call active SLAM, simultaneous localization mapping, as opposed to passive, right? So these agents go into their environment and then they reason about the environment in such a way that they can then map better. In other words, they can reason about their uncertainty as well as the other objectives that they have to accomplish. These neuromorphic architectures are up and coming, event-driven, so to speak, and the benefit they have is that they're very energy efficient. And so they're also more complex because they are event-driven, but this is an up-and-coming technology. In the lower left-hand corner, I mean, this has been around for a while. Optimal adaptive control, as a control theorist, this is our bread and butter. For those who are aware of robust control, this symbol, this picture should be nothing new to you. But there's still advancements being done, like especially with like model predictive control. We're finding ways of putting these, I would say, rather sophisticated optimization algorithms into teeny tiny microcontrollers. Like, I don't know if you've heard of Tiny MPC. If you haven't, highly recommend looking it up. So Zach Manchester is a professor, and he recently found a way to take OSQP and shrink it down into a microcontroller, and he was able to do some very aggressive drone flights with that. So very cool technology. Task and motion planning has also been around for a while, but it still presents a lot of fundamental challenges, especially when we try to scale and do lots of agents all trying to do work in potentially a formally verified way. Probabilistic inference has also been around for a while, but nonetheless still highly relevant, especially with things like visual odometry and active SLAM. And then lastly, the foundation models, right? The up and coming, the chat GPTs, the Google RT2s, VLA, vision language action models. This is like the big black box where information goes in, action comes out, and it's scary how good these things are. So as you can see, there's a huge amount of technology that's actually going on. It's hard to grasp every little thing, but nonetheless, the key here in these 2 bullet points really drive it home is that they're becoming more complex, and in order to become more autonomous, and as these become more complex, gaining trust in them just becomes so much more difficult. So that kind of frames where we're going, where this talk is going. But let's just ground ourselves a little bit. Why do we actually need this notion of trustworthiness? Well, we've needed it for a long time. So you can see all the way back in 2011, here's a quote from AFRL, and you can see we needed it back in 2011. Now fast forward in time to 2022, a quote from Heidi Shue, we still need it. So, I mean, is this implying that just nothing's being done? In fact, I want to push back on that because a lot is being done. But the problem, and I mentioned this before, is that the technology is just growing so fast that we just can't keep up. And so, I mean, that's really just the challenge here. And so, I'm just going to point out some important pieces from these quotes. You can see, like in the first bullet point, suitable V&V methods, verification and validation methods, and the notion of being certified for use. In the second bullet point, you can see the connection with human robotic interactions, falling into things like understandable autonomous systems behaviors, and just going back to the fact that we have to be able to understand how these machines are operating. And the third bullet point, trust, that's where that really comes into play. And this notion, this more subjective notion of how do we actually trust these things. And then, in 2019, measuring the trustworthiness. And then even in 2020, we have assurance, cyber physical systems indicating that these things are very software centric, and that we need to ensure things like quote unquote correct operation. So really, I mean, this definitely highlights the need for trustworthiness. And again, because the technology is just growing so rapidly, that is the major challenge here, is that we just need to scale up in order to actually make sure that we can assure these technologies. Okay. So now I'm going to get philosophical on you. Let's talk about trust and trustworthiness. And again, there's really no great definition for trust and trustworthiness, but what I do want to say is that trust, as I see it, is an attitude. It's a human subjective attitude that involves both vulnerability and reliance. And then trustworthiness is a property or a trait that we ultimately assign to these things. It could be a human, could be an agent, but nonetheless, that is the core distinction between the two. And so there's no universally accepted definition, but there are lots of different theories. And so if you're interested in the subject, I won't belabor it too much, but if you're interested, highly recommend reading this article by Carolyn McLeod on Stanford Encyclopedia of Philosophy. It's also great reading, puts you to sleep if you don't like it. But nonetheless, I think there's a lot of value here. And I actually think there's a lot of value in thinking about this from the perspective of a philosopher. So on the left, risk assessment theories, I think these are natural, especially all engineers, we all think about notions of risk, right? And so the general idea here is that trustworthiness is just based on the truster's perceived risk of the trustee acting reliably or unreliably. The problem here that the article points out is that, well, I mean, it's indistinguishable from reliance. Basically, the focus on whether or not the trustee is willing to act irrespective of its underlying motive. And that's the interesting part about this, the motive. And I mean, it makes sense when we talk about it in terms of humans, but when we talk about motives with artificial intelligence, that's tough. That's really hard to think about. And so as we extend the concepts to these motives-based theories, the non-motives-based theories, that's when we start really getting down the philosophical rabbit hole where things start to become more challenging. We'll leave that to the philosophers, but nonetheless, I still think there's a lot of value in thinking about some of these other two, the two on the right. But for nonetheless, I think it's more pragmatic if we just think about it in terms of risk. Okay, so diving into, all right, so we know that trustworthiness is related to risk, but what are some of the characteristics associated with trustworthiness? And honestly, I've had so many debates with so many people, and at this point, I'm just like, I'm tired of debating on what trustworthiness actually is, because I think NIST has actually done a really good job. So they recently put out in 2023 this risk management framework for AI, but I think it can be steered rapidly toward autonomy. And this is how they've bucketed it in terms of what trustworthiness characteristics actually are. And I'll let you read that banner, but I've called out a few specifics. And I think, as no surprise, safety and safe is one of the top, right? We want to make sure that these things don't lead to a state in which human life, property, et cetera, are endangered. But I do want to emphasize that it's not just all about safety, right? We have to have other factors. Otherwise, we're just going to be risk adverse. The machine is just going to sit there. It's going to recognize that it eventually has to solve the trolley problem. If you don't know the trolley problem, it's basically you have one choice or the other, but both are eventually going to kill somebody. And it's going to say, I'm not even going to operate because I can't figure out that solution. So Point being is that these machines have to be performant as well. So it can't just all be about safety. So I briefly talked about the 3 Rs: reliable, robust, and resilient. I think these are really important, and they all sound the same, but they all have distinct definitions. So robustness, I think about that, as a controls engineer. If I'm designing a robust controller, I have an operating region the system is going to operate in, and I want to make sure my policy, my feedback control law will operate and be stable or performant in all of the operating regions in which I'm designing it for. Resilient is the after the fact. I put it into the world and it's operating in a region that maybe I didn't design it for. Can it actually fail gracefully, or even accomplish the mission and still be resilient despite the fact that not everything goes as planned? And lastly, reliability. I think that's really just kind of like mean time between failure. It's like, does the thing actually just do what it's supposed to do in real life? Quality would be a good idea for assessing that. And then lastly, valid. So I had to scratch my head on this one a bit. So I know we have a lot of software engineers in here, and you're probably all well-versed in V&V, and I hope you're scratching your head too, because valid, verified, I mean, they're distinct, at least from my perspective, but for some reason NIST and their definition of valid almost kind of mixed the two, so to speak. But I think that was the intent. I think they wanted one word to fully encapsulate both V and V, and that was my takeaway here, is that they have to be verified, and they also have to be valid too. So again, I think all of these are fully legitimate. I think these are great characteristics of autonomy. I think the RMF is a great source to read if you have the time, and it's definitely some great recommendations in there too. All right, so now let's dive into what's actually challenging here. So I've divided this into 9 challenge factors. And so obviously the one in the upper left is the big one, right? As I mentioned before, these things are going out into the field, they're learning about their environment, they're making decisions, and they're potentially even coming back to future generations of autonomous systems. And so because of the fact that they are now subject to what they experience in the environment, we have to make sure that when they learn, they're learning safety. They're learning things that aren't necessarily going to create maladaptive behaviors, for example. So non-deterministic algorithms, I mean, these have been around for a while. Like we talk about like RRT star, for example, which is like a path planning algorithm, and that has probabilistic guarantees, but nonetheless, it's still challenging to enable these probabilistic guarantees, even when you think about things like formal methods, for example, and you start thinking about like probabilistic forms of guarantees, that can be very challenging. Complex software, I don't need to belabor this. I think we can all appreciate the fact that software is very hard to assure in general, AI or not, and nonetheless, it doesn't make our life any easier. Black box algorithms, I already mentioned, connectionist approaches, neural networks, the sheer fact that we have lots of data, we have black box algorithms, and they work great sometimes, and when they don't work great, we have no idea why. Environment and complexity uncertainty, that's obvious. And then mode confusion. I mean, this is getting to like the human machine teaming, the fact that we need to have calibration between the autonomous system and the human. We have to make sure that if the human understands the capabilities of a robot, that it's accurate, and vice versa. We have to make sure that the machine understands the capabilities of the human too. So is the human talking to an O6 or an O1? Is it talking to somebody low on the chain or high on the chain? And that is going to matter. So we can take these challenge factors and boil them down into like resulting challenges. So what I like to think about, what are the guarantees, right? And what are the assumptions that enable those guarantees? And that's really a fundamental challenge, especially with like non-determinism, learning-enabled systems, and so forth. Ensuring explainability to a diverse audience of various backgrounds, going back into the O1 versus O6, does the person need to have a PhD to understand why an autonomous system actually did something, or can they be a high school student? That's a huge challenge. Calibrating notions of trust, I already talked about that, making sure that the human and the machine understand each other and can actually convey notions of trust between the two. Fourth bullet is just going into standards, requirements, metrics. This is all the stuff that we, as software engineers, we really think about. But nonetheless, the sheer fact that AI is just growing so quickly, it's making it hard to actually develop standards in order to match the rate. And then lastly, this somewhat related, scalable and cost-effective TEVV. So as you can imagine, as the state space explosion happens with a lot of these algorithms, being able to test them in a reliable way is just cost prohibitive. It would take so much time to actually ensure that every edge case is handled and so forth. Okay. And then lastly, how much trustworthiness is actually necessary? So I have a lot of debates. I work with a lot of people who do flight software and a lot of people who do rapid prototypes and just want to get something out into the field to meet a critical need. And it's often that, you know, the people who are putting things up into space will come back and say, well, how do you know? What are your guarantees? And the people who just want to put stuff into the field are just like, well, you know, my risk tolerance, right, is a whole lot lower than yours. And I think this needs to be talked about more, is that we can't all come to the table and say, here is just one universal guideline on how to assure these systems. And this goes back into the notion of risk, right? Because we need to make sure that you know, if we're putting something into space, well, yeah, that's absolutely a higher risk tolerance than just doing something very quickly to meet a critical need. So the point being here is that yes, safety critical systems require substantial evidence, but not all systems are safety critical, and so necessarily, like that notion of trustworthiness has to reflect on the risk. And so I do want to mention too that there are application specific standards, specifically geared more toward like autonomous vehicles. But I do want to really mention, I think we can all agree on this, is that software specific standards are still highly relevant. I often tell people that software is the language of robotics. There's really no way around that. And I get very concerned when people do autonomy and they have safety critical code that is written in Python, for example. And so I really do think that we still need to find and have value with these software specific standards, and the autonomy community really just needs to be more aware of them. And then lastly, I do want to mention too that assuring autonomous systems is not free. It costs both time and it costs money. And my personal fear is the opportunity cost. I fear that we're going to set the bar so high and the amount of trustworthiness that we see necessary that our peers, our adversaries are just going to basically go off and just do it, and we're going to be forced. So my opinion is that we need to be gradual about it. We need to take small risks here and there, but if we don't, then we're gonna lose the opportunity, unfortunately. Um, okay, so I'm gonna briefly go over this because I think we all, I don't know, I would not be surprised if somebody had this tattooed on their arm, but basically like, how do we do development process for AI-enabled systems and again, software-enabled systems, right? And so I've shown like a spiral diagram here. We design, we build, we test, and then we approve. We go back and iterate. So these 4 areas, this should be nothing new, right? We do static analysis, we do unit testing, inspection and code reviews. This is all the great stuff that we do as software engineers, right? Although it's application dependent, I mean, I would almost say that some of this is universal in the prototypes that we develop. But I mean, how many of us actually do FMEAs, right? And we think about the underlying risks of the software that we develop. And so these are some risk-aware considerations, especially with AI in the loop, that we really need to start thinking about. And so we've got like identify AI system attributes here, like what's our tolerance to failure and risk, our degrees of independence, what are the boundary conditions and use cases. So I think these are all very useful things to think about. And then lastly, what is this quote unquote good enough? And I put that in quotes because again, it's application dependent, it's organization dependent. Some of it might be guided by policies and regulations. So is it good enough? Then you can quote unquote consider it assured. If it's not good enough, you make it acceptable to humans and you consider it accepted. I don't fully agree with this chart, to be honest, because I honestly think that you can be assured and still not accepted by humans, right? So I think these are 2 parallel processes that I think that, assurance and acceptance by humans are not necessarily one-to-one. I could have a full mathematical proof that a system will operate as intended, and I would probably still be skeptical, depending upon, if my life were on the line, right? Um, but nonetheless, I think this is a very useful process, and it's one that we should definitely adopt. And then lastly, I would be remiss not to talk about this. And so since this is ending up on YouTube, I'm not actually going to say the name of this paper. I highly recommend reading this paper. And again, going back to philosophers, right? These 3 authors, they're all philosophers at, I believe, University of Cambridge. And this is really just going off the fact that these LLMs, these large language models, aren't really quote unquote hallucinating. They're actually, I'll abbreviate, they're BSing. And so there's a philosophical definition of BS. There are 2 varieties, there's soft and hard BS. But really what we're getting at here is the fact that these LLMs generate their outputs, quote unquote, not by an intent to deceive, but instead by a reckless disregard for the truth. And so for those who don't know, these autoregressive LLMs, by their design, by their foundation, are just token predictors. You give them an input, and then basically they're just trying to complete the sentence based off of terabytes of text that they've seen before. And so at that end, they're just generating text. There's nothing to actually verify that these things are generating valid text or even coherent English sentences. And so really that's what this article is getting at. And so they prove that they are soft BSers, meaning that they are, they satisfy this. But the hard part is the hard definition of BS, which actually is intent, right? You have to show intent of this reckless disregard for truth. And this is getting to the more philosophical notions of, well, what's intent? It's just a software algorithm, right? It's not a human. But nonetheless, the point that I want to make here is that we just have to be careful because LLMs are useful, right? I use them. I'm sure we've all used them in some regard. But the underlying technology probably isn't trustworthy, so to speak. And so we're going to need some guide rails. We're going to need some help in order to make sure that these technologies will actually do what we need them to do, because whether or not we like it, they're going to be used. Like it's a matter of fact that their performance is great most of the time, but when it's not, we need to have those guide rails. Okay, so let's see. All right, so I do have a case study for you. I'm just going to briefly go through this. I think some of you will resonate with it. For those who have a machine learning background, there's not going to be anything new here. It's probably just going to be information that you've already seen, but nonetheless, I just do want to frame this, and it really will just show some of the problems with some of these deep reinforcement learned policies. So we're just going to dive into this AAM case study. AAM is Advanced Air Mobility. So the point being here is that we had 2 case study objectives, and this was done with NASA, was to not only create a simulation environment, but to also evaluate and verify some of these AI ML-based techniques for in-time aviation safety management systems. So really just going at this notion of contingency management and evaluating AI frameworks. And so here's an OV1 kind of showing what we're getting at here. You can see the vehicle in blue. It needs to get to its landing point, its vertiport, and it's going to follow an original route. This can be generated through anything, RT, A-star, what have you. But the problem is that it has to do this contingency management based off of what it's seeing in flight. So it could take, unfortunately, path A, where it decides, well, I actually can't get to my original landing site, maybe because there's bad weather in the way, so it has to divert itself and go to a different vertiport. Or maybe in the B case, it has to make an emergency landing. Maybe, the energy system failed and it has to go land in the middle of the forest somewhere. Or in C, maybe there's, an adversary coming in and it has to do some collision avoidance and divert itself. So all of these examples are just notions of contingency management where reinforcement learning could potentially make a difference. And so that being said, if any of you are interested in ways of doing multi-agent reinforcement learning, we've actually developed some great software that scales very well to things like supercomputers. We call it AAM Gym, Advanced Air Mobility Gym, very similar to things like OpenAI Gym and Gymnasium. But really what we try to do is kind of standardize the training and validation of some of these algorithms. So if any of you are interested in that, happy to point you in the right direction on how to leverage all of this. But as you can see from the block diagrams, it's just a very natural way of scaling what we call workers, which are ways of training these agents and then extracting metrics from those and doing faster than real-time simulation. And so this is what the general simulation framework or environment kind of looks like, where we generated airspace scenarios based off of things like demand modeling, and that really governed like the routes and the landing points. And then we also have network modeling too. So in particular, we are looking mostly at New York City. And then we also have some environmental factors too. I already mentioned energy, reserve, uncertainty. There's also notions of hazard. You can think about hazards, things like GPS denial, for example, and then weather uncertainty, which is more stochastic by nature. And then from these two, we've then extracted what we call algorithmic approaches. We have the baseline, the heuristic approaches, rule-based logic, regular path planning, and then we have reinforcement learning. So we have, the classic approaches, dynamic programming, and then we've also got the more deep approaches through neural networks. So just a little information on the heuristic approach. So we did borrow this from an actual, heuristic agent that is used in real life. And you can see one example of this heuristic agent. If you zoom in a little bit right into the deep heart of New York City, you can see the original path in red, and that just drives it straight through this hazard point, and then the heuristic agent follows the red until it reaches the hazard and then diverts itself. Nothing complex here, it's just a rule-based algorithm, that's all. All right, so at the time this was done, these were relatively recent reinforcement learned algorithms. So D2MAV was one that was specifically developed for this, specifically geared toward multi-agent reinforcement learning. And then SAC is actually a widely used approach, soft actor critic, and we use the discrete action space version of this. I won't dive into the distinction between on policy and off policy. There are pros and cons to both in terms of data efficiency and stability and so forth. But nonetheless, really just the point I want to make is that we tried both, right? We tried two different algorithms of different genres, and then they both use the same network structure. And so the highlight here is that, yes, it is deep, it is attention-based, and very difficult to ensure explainability here, but nonetheless, it was a deep structure. All right, so as far as the experiments go, these agents were trained using what we call curriculum learning, and this actually is very an intuitive way of training these agents. So you can see, in first grade, this agent learns to reach the destination. That's basic fundamentals. And so as soon as we can verify, or at least through simulation verify that it has learned this task, we can then add complexity. We can scale up the policy and teach it something more complex. So then it reroutes to an alternative vertiport due to reduced energy levels. And once it shows that it can actually do that, then we keep adding more complexity, and that is the fundamental of curriculum learning. You just keep training it on more and more complex behaviors over time until it does, the very large task that you want it to do. This took a very long time. It took a lot of compute, a lot of power. Let's see, 266 million hours of flight data, 798 million operations, weeks, if not months, of total training time. It took a long time. And so as you can see, it's not just like, it takes a long time. Yeah, that's all I'll leave it at. And so you would better hope that, the performance was worth it. And really, it was. So I won't belabor this too much. You can see that the deep reinforcement learning agents actually do quite a bit better, 91.6 to 95.2 with a 2 sigma of 1. And so they make it to the vertiport, and the heuristic agent actually has to reroute 76% of the time. And so really what we're finding is that the deep reinforcement learning agent does better most of the time, but when it doesn't, that's when we start scratching our heads. And so this slide, operational suitability, is just highlighting the fact that sometimes they do really weird stuff, very weird stuff, and it's really in the outliers, right? They learn the task, but in the outliers, they do very strange things. And so what I'll call out, let's just compare this to the heuristic agent. Heuristic agent takes off, says, no way I'm going through that. I'm just going right back to home. And so it's overly conservative. We look at this SAC-D agent, soft actor critic, in the green, and it actually drives toward the hazard, and then it takes a roundabout area, like a path, and it's basically saying, I'm not going anywhere near that thing. And then eventually it tries to get back onto the route, and it drives almost right into the hazard. And you're just scratching your head like, okay, so it's permissive, or it's risk averse here, but then it's risk seeking in other cases. Like, why would that actually happen? And then lastly, the D2MAV agent, basically, like, it follows the original route and then skirts along the hazard, and it just drives right through the hazard. And so you're just like, why? Like, the performance is good on average, but why are these outliers showing up? And why is it suddenly deciding to do that? And so really that's the challenge, right? Is trying to figure out, being able to do explainability studies to actually figure out why these things are doing what they're doing. And so, yeah, just to summarize, like, these deep reinforcement learning agents, they take a lot of time to train. And one of the complexities about training them is sometimes they also forget too. So while they're learning these tasks, and you can see one example here between the second task and the third task, that it forgot how to do task number one. And so what we call this catastrophic forgetting, which really just makes the whole complexity of training these things even more challenging. And there are ways to get around this nonetheless, but nonetheless, like it learns task number one, which is the most fundamental. It goes to first grade, passes it, and then suddenly forgets how to do arithmetic, right? And so that's just really highlighting some of the challenges that we have here. So again, that was just a case study really framing some of the major issues that we're seeing, leveraging these deep reinforcement learning policies and approaches. But nonetheless, there's good news because a lot of very smart people are thinking about things like this. And so I am in no way able to fully cover the entire scope of how people are enabling trustworthy autonomy. These are 5 areas that I personally think are particularly interesting, and particularly the lab, MIT Lincoln Laboratory, is really focusing on. And so formal methods, it's been around for such a long time, so many decades. And it's only recently, perhaps within the past couple of decades or so, really taken off in terms of task and motion planning. Basically being able to combine these 2 very difficult problems, tasking and scheduling of multiple agents, as well as motion planning. And for those who don't know, that's a continuous and discrete optimization problem, which, is a very challenging problem to solve. And then tack on formal verification and actually getting formal verifiability on top of that. But nonetheless, these are actually methods that are coming to fruition and actually being used. And I have an example of that coming up in a few minutes. And so the great thing about that is that it's actually a bona fide proof, right? It's an actual certificate that says, yes, this will actually work. And then going into actual certificates for perception, for example, and I honestly think that this is an area that's probably less covered, but nonetheless, it's still growing. And so I've highlighted here what I call certifiably correct collaborative SLAM. And so this is really pioneered by professors like Luca Carlone at MIT, David Rosen at Northeastern University. And what you're seeing here, and I'm actually going to replay this video because I just think it's really cool to see, is you're seeing a solver basically trying to merge maps together among multiple agents. But the beauty here is that it's certifiably a global optimum. And so oftentimes these SLAM packages will use local solvers, and sometimes you just, at the end of the day, you get a big yarn ball of maps, and that's just because they're converging to a local optimum that makes no sense. But by using advancements in polynomial optimization, you can actually do relaxations that convert them into semi-definite programs, which have convexity associated with them, and then you can basically get gaps in terms of the optimality, and you, at the end of the day, you get a certificate that says, yes, this is the global optima, and you see that kind of turning into an actual map. And so I just think this is a great path forward, but it's still relatively new. And so in the third area, safety supervisors. So I'm sure, I mean, if you haven't heard of the term control barrier function, this has been around for at least a decade now. A lot of people are doing development on CBFs, but nonetheless, just like, as a control theorist, the holy grail is being able to find your Lyapunov function for a very sophisticated nonlinear system. CBFs are no different. It's very challenging to find an actual CBF for a highly complex system, but we at MIT have been working with Chichu Fan, also at MIT, on what we call neural control barrier functions. So the whole premise behind a neural control barrier function is that you can actually use machine learning approaches to find the barrier function. So she's extended it to GCBF+, which is actually the graph neural network approach. And what you can see here are a bunch of crazy flies all working together, doing dynamic collision avoidance on obstacles as well as themselves, and reaching a final destination state. I also want to call out some work also done at MIT. Anu Anuswamy has been working on integrating adaptive control. So one of the major issues with control barrier functions is that they are model-based. And if you don't have a good underlying model, then where's your certificate? And so by leveraging adaptive control, you can actually adapt in real time, get a better model, and you have a much more reliable certificate. So she's actually been able to show multi-agent consensus with control barrier functions and adaptive control. And at the end of the day, you get a very nice mathematical proof showing correct operation. And the fourth, resilient networks. So this is dynamic crowd vetting in collaboration with Stephanie Gill at Harvard. And the whole premise here is that we make a lot of assumptions on the underlying network topology and whether the actual agents are friendly or not. And we often assume they're just all collaborative, but thinking about the very first slide that I showed, we're going to have some people on our networks who might not actually be trustworthy, and these agents are going to have to think about that. Like if they're receiving information from somebody on the network, Can they actually trust it? And that's what I love about this work from Stephanie Gill, is that it's actually trying to solve that problem. So using information that these agents are collecting, they're able to then reason notions of trust amongst themselves. And, this protects against things like Sybil attacks or Byzantine attacks, where, cybersecurity is really a problem, especially with software-centric systems. And then lastly, dynamic games, I think, is a really interesting area, and specifically with stochastic dynamic games. And so this is an area that we at the lab have been really thinking about lately, specifically in terms of software package called IOQ Games. But nonetheless, we really do think that there's a lot of benefit in leveraging some of these more formal approaches to playing multi-agent games and enabling that at scale. So again, these are just 5 areas that I see being particularly noteworthy. In no way are these exhaustive at all, but nonetheless, I think it's important to be aware of these. Okay, and so lastly, I'm just going to talk about some really cool projects that we're doing at the lab. And I wish I had more time to go over all of these, but nonetheless, we at the lab are really trying to think about how do we actually do verifiable multi-agent autonomy at scale. And I do want to credit the 2 PIs on this particular work, Zach Serlin and Kevin Leahy. They're the brilliant minds behind these 3 particular areas. So I'm only going to talk about the one on the right, but nonetheless, I do want to mention the 2 on the left. So the one on the left is a program called DCAF, Dynamic Collision Avoidance in Flight. And this goes back to that notion of neural control barrier functions again. We have this very complex, what we call exotic dynamical system. The F-16 is a good one. You can think about CCA, whatever, complex aero system that is having to do collision avoidance and is highly nonlinear and suffering from things like fuel slosh and so forth. And the question here that we're trying to do is to generate verifiable control filters and safety filters in order to ensure correct verifiable operation. So again, that is DCAF. I'm happy to talk to you more about that if you're interested. The one in the middle, program called Maestro. See if I can get this acronym right. Multi-application for explainable, safe, temporal logic for reward-based objectives. They're really good at generating these acronyms, but nonetheless, the gist here is that there are 2 aspects. Basically, if you have a whole bunch of time series from a potential, I'll call it opponent, maybe you're playing capture the flag, and how do you best characterize what your opponent is doing? What is their strategy? So you could think about it in terms of model-based approaches, but what these 2 PIs did is they basically were able to turn time series information into formal logic, temporal logic. And so with that, they can actually take the opponent's policy or the specification that they believe that the opponent is following, and then they can use that as synthesis. So they take that opponent's specification, put it into their own synthesis algorithm, and then they come out with a new policy synthesis or a new policy that has been synthesized, and they are able to basically play the game in an optimal way such that they can actually win. So you can think about the various applications here, like flanking maneuvers, and so to speak. We use the capture the flag game because it's really easy to get out into distro A, but nonetheless, let your imagination run its course. And then lastly, the one that I actually do want to dive into, just because I think it leads to some really cool math and is also very cool to show in demonstration, is heterogeneous coordination for C2. So this is a program that we call SHARC, Scalable Heterogeneous Autonomy for Resilient Coordination. And you can think about this like I have lots of stuff that I need to get from point A to point B. The stuff goes into the environment, some breaks down. Maybe I need to change what the stuff needs to do. And how do I do that scalable? In a scalable way. And when I talk about quantities, I'm thinking on the orders of thousands. Like we want to make sure that we have so many agents into the field and we can actually coordinate them all in a scalable way. And so one potential example here would be like maritime domain awareness. And so just diving into what we call SHARC. So you can see on the left that we want to make sure that the operator is able to interact with the system. So the operator gives a list of tasks and requirements to the system. So the way that this is done is through a temporal logic specification language that we have developed. It is a fragment of temporal logic, signal temporal logic that we call capability temporal logic, or CATL. And so the user will specify a cattle specification, and I'll show an example of what that would look like. And then based off of that cattle specification, the system, the Shark system, ultimately divides the team into roles and subgroups. They go off and do their thing, but in the fourth column, you can see that maybe the agent needs to retask the systems, or maybe an agent failure happens and now they suddenly need to dynamically replan. And so using this framework, we're actually able to do this in a scalable way that is also resilient to things that they encounter, but it's also based off of formal verification, formal methods that enable some notion of verifiability. And so here's what we call the hierarchy. So starting at the top, obviously the operator has input, again, through cattle specification, goes through a translation process where we turn it into more machine interpretable tasks, and then it goes through decomposition and distribution, and then it goes through, distributes to different plans and planners, and then that goes to the underlying motion planners and safety monitors that will enable replanning. And what I want to call out here is that this is not a unidirectional arrow, it's bidirectional. So this pyramid goes down, but it also goes up to the root node as well. And this allows for that dynamic replanning, which is so critical in order to enable resilience and robustness. So again, I mentioned cattle. And so if you look in the upper left corner, we have what we call a task library. And you can see some examples of what this task library might actually look like. So you can say things like raster site A within 20 minutes. So you can see flavors of signal temporal logic coming out of here, but nonetheless, it's more geared toward capabilities. And so we hope that, based off of this specification language, that it's more easy for operators to manage. And then from that, we can actually create a cattle specification, which then gets encoded into an integer linear program. So for those who are aware of LTL, for example, your LTL can be naturally translated in things like a Buki automata, which you can then use to verify your system. And so that's very similar to what's happening here. And then going back, you have the common operating picture shown in the left corner. So from that common operating picture, that's your environment, your dynamics, the number of agents that you have. You can also get an integer linear programming encoding from that, and you combine the two. You combine the specification with the integer linear programming encoder, and you can do synthesis. You get a plan from that synthesis just by doing a numerical solver. If you use Gurobi, that's great. It doesn't matter. It's basically anything that you want that can be able to solve some of these mixed integer linear programs. And from that, you actually get what we call correct by construction plan. In other words, it's guaranteed to satisfy the capability temporal logic specification. And if it turns out to be infeasible, you get a check mark that says, I can't do this, which is actually very critical because a lot of algorithms that aren't formally verifiable will just say, yes, sir, and they'll go off and then misbehave. And what's also great here is that even if the plan turns out to be infeasible, you can get minimally violating solutions. You can get an option. So you can get notions of okay, I wasn't able to do this, but how important is doing that? And you can have the operator basically modify the task, the underlying specification, even if the plans are unfeasible, to ultimately create a more feasible task. And so I do want to show this demonstration. So this was done in collaboration with Mike Benjamin, a professor at MIT, out on the Charles River. So although it is surface vehicle based, it naturally extends quite well to other domains. In fact, it's relatively domain agnostic. So if you wanted satellites, if you wanted underwater vehicles, the key here though is the need for communication. So that's something that we're actively thinking about, how to best amend this technology to allow systems to operate in regions where maybe they can't communicate with each other for long periods of time. And that obviously makes replanning more difficult, and so to speak. So you can see here basically just an example of these agents all going from point A to point B, and they're all dynamically replanning, performing various missions within these certain areas. And again, all formally verified to meet the specification. Okay, and I will show, so we do have hardware in the loop testing capabilities. It's very important, that we're able to simulate these things, and not just simulate, but also test that the hardware works. And so we're able to develop some simulation capabilities that we can perform at scale. And then you can actually see the agents going off and doing their own things. Here we only have a handful, but again, what we're trying to really do is do this majorly at scale, like thousands of agents minimum. Okay. All right. So with that, I'm happy to wrap it up. What I really want to do call back to is the fact that AI is growing quickly, whether we like it or not. The need for AI is still going to be it's going to be a necessity, and our ability to assure the AI, so to speak, is going to be very challenging and also a necessity. I do want to mention too that the amount of trustworthiness is highly dependent upon the underlying risk in the application involved. Safety critical systems obviously need a lot of evidence in order to assure them, but nonetheless, if you're just doing rapid prototyping where the risk is relatively low, then you actually don't need a whole lot. And again, it's tied to the cost and the time. And if we are too risk averse, then we're going to have opportunity cost that we lose out on. So obviously there are a lot of complexities in enabling trustworthiness. Non-determinism, non-transparency. We have to make sure that these systems are explainable to humans of a diverse audience. So again, the 06 versus the 01, the PhD versus the high school student, and that is a fundamental challenge that a lot of intelligent people, very smart people are working on. Diving back into this notion of trust and what is trust and trustworthiness, well, there's really no correct definition, but nonetheless, I associate it with risk. I think some of the other motives-based or non-motives-based theories are interesting, and maybe they'll come to fruition in the future, but nonetheless, just tying it back to risk, I think is very important. And then we can characterize it through things like the NIST RMF framework, which is like safety, reliability, robustness, resilience, validity, and so forth. And so, yeah, past 5 years, we've seen incredible growth and verifiability for autonomous systems. It's still growing. We're still catching up, so to speak, especially with the capabilities. And I've noted several times that, connectionist approaches, symbolic or neural approaches to artificial intelligence have really been challenging, but we're seeing a lot of frontiers in things like neurosymbolic approaches, basically taking our old friends from the 1980s symbolic approaches, which really didn't scale and ultimately led to an AI winter. And we're combining those with the symbolic approaches, and we're actually seeing a great merger between the two. And honestly, my opinion is that that's probably where the future is going to be, is in neurosymbolic approaches. So keep your eyes on those. Lastly, I showed you a few different demonstrations of several projects that the lab is working on in terms of verifiable multi-agent autonomous systems. By no means exhaustive. There's a lot of work going on elsewhere too, but nonetheless, I just want to go back to like let's have conversations about this, and it's not going to be solved overnight, and it's not going to be solved by one person. But the more that we talk about that, the more we work together, it can be more manageable, and we'll actually get this done. So thank you for inviting me. I'm happy to be here and answer any questions. Thank you.
I'll go online. There is a question. Does robust planner in chart have any notion of dynamic agent hierarchy or leadership?
It's a great question. Yeah. So it does incorporate notions of motion planning, but it's not going to incorporate, I would say, extensive dynamics. So, I mean, if you're thinking about things like, oh, the nonlinear dynamics of an aircraft, it's not going to necessarily enable that. In fact, that would be a very difficult thing to scale. So it does assume very simple dynamics, very simple kind of kinematics. And yeah, that is actually a limitation, right? You have to cut it off somewhere in order to make it computationally tractable. And that's just where we chose to cut it off. Good question.
Yeah. Thank you for the great talk. So could you explain more detail about how can we model uncertainty created by dynamically changed environment or even adversarial attacks?
That's a $1 million question. How do we characterize the uncertainty, especially in the environment? And that's great. I don't have a great answer to that. I would say that the more data that we have in order to guide our simulations, I think will be quite valuable. And so that obviously goes into things like dynamic verification. It's not truly static verification. You're not going to get, mathematical proofs from that. But I do think that there's a lot of data out there. And I also think there's a lot of validity and usefulness in adversarial simulations as well. Basically using things like deep reinforcement learning to learn how to break your code. So we see, if you're aware of like simulations like Carla, for example, which are used in like the autonomous vehicles community, you see approaches like anti-Carla, for example, which are basically taking Carla and designing policies that where their environment can actually find those edge cases through machine learning. And so I don't have a great answer to your question, but nonetheless, I still think that like adversarial simulation approaches are probably going to be valuable and will ultimately lead to effective ways of kind of finding those edge cases. But great question. That's hard. Yeah.
We have another question, Miles?
Hello, thank you. And I apologize in advance if I may have missed it when you're talking about the risk-based motives. But for humans, there's threat of loss, injury, even death. Is consequence play a role at all? Like what does an autonomous agent actually lose if it fails?
That's a great question. And so that really boils down to the notion of cost, I think. What is the relative cost of that particular asset? And I mean, obviously, if the cost is relatively low and there is a relatively strong focus, you see this in like Ukraine, for example, with the ubiquitous use of low-cost autonomy, you're right. Yeah, there's really no loss, so to speak, assuming that it's not eventually going to lead to a consequence that will cause loss, like loss of human life, for example. So no, consequence absolutely is. And I think the challenge then is being able to predict that consequence too. And this goes into like the environment modeling, right? How do we actually learn to predict the consequence? And then you can think about like the trolley problem, right? Eventually, like these systems are going to have to go and face the option of I have to do A or I have to do B, but no matter how I do it, it's going to lead to a cost of life. So no, I don't have a great answer, but no, consequence is definitely something that is very tied to risk and something we need to think about. Yes.
We can take one more. Yep.
So if everybody in this room, let's say, come up with some sort of AI models, how would you go about evaluating or VNV to say, hey, that is a trustworthy? And if I look at the bullet, like a third bullet and the sub bullet, it says trustworthy is characterized by safe, reliable, is it robust? I mean, everybody in this room is a part of in the Fly software community, right? Is it any different from AI ML to Fly software? I mean, that's the same thing. When I build a software as a part of, let's say, Fly software engineer, I want to make sure that it's safe, it's reliable, it's robust, and it's resilient, it's valid. So do you have any thought on like how, like some sort of a framework to say, these are the things you want to, kind of check off and to say, it is a trustworthy AI/ML?
So that's difficult because so then we're talking about certification, right? And so I think there are a lot of lessons to be learned on how do we actually certify real autonomous systems that are going on right now, like in San Francisco, like with Waymo. I think the legislation is actually, and you can dive into like researchers like Philip Koopman, for example, who, I mean, this is their bread and butter, things that they think about. And so I do think that standards are coming into play with how to assure, so to speak, that particular application of autonomous systems. So as far as flight software goes, I think there would be a natural extension. Obviously, the dynamics are different. San Francisco City Metro is a lot different than the environments that planes would be encountering in the sky, or satellites would be encountered in outer space. But nonetheless, I still think there's an extension. But nonetheless, I don't think there's the same level of an equivalent to flight and space. I just don't think it's as mature just yet. But nonetheless, I still think it's an area that we as a community really need to start diving into and having conversations about. And again, there might just be areas of research that I'm just completely unaware of. But nonetheless, I just don't think it's as mature, so to speak, as the autonomous driving vehicles right now. So.
Thank you very much. Give it up for Trevor.